Okay, so in a week we will have the last lecture that will be devoted to quantized electromagnetic field. And today I will talk about solutions of Maxwell equations from the point of view that is natural when one uses the Riemann-Zilberstein vector. So let me remind you again that in terms of the Riemann-Zilberstein vector, Maxwell equations are just one complex equation for the time evolution and the divergence condition. And we learned about this vector a bit. One of the things that we learned was that it can be represented in terms of its Fourier transform. For convenience, I include this vector. Then there is a polarization vector here, one polarization vector, and the sum of two terms. One is coefficient we call f plus of k of the wave vector, e to the minus I omega t plus I k dot r, and another one which for future convenience I will denote coefficient by the star coefficient, meaning complex conjugate. And I explain how this comes about from the straightforward Fourier transformation. The face here has the opposite sign. And I mentioned at the end of my talk last week that Whittaker had shown that the solution of Maxwell equation can be expressed in terms of two real solutions of the wave equation. The wave equation is 1 over c squared. It's called also the D'Alembert equation, minus this three-dimensional Laplacian acting on some function called chi of r t equals 0 is the wave equation describing propagating waves. Now here are the factors that are also familiar from waves. They represent waves running in positive z direction. So the question is, where is the negative z direction? Of course, f of k is arbitrary, so we can take k in the opposite direction to the z-axis, and then we'll have the wave running in the opposite direction. Whittaker construction can be easily deduced from this formula, provided we say something about this polarization vector. As I said last time, it is convenient to choose this polarization vector in the form 1 over the normalization factor, which happens to be square root of 2 times kx squared plus ky squared times k, which is the length of the vector k. Look at it, is this, of course, k stands outside of the square root, so the dimension of this denominator is k squared, and the numerator also has the same dimension. The numerator is minus kx kz plus I, the length k and ky, minus k y k z minus I k x kx squared plus ky squared. So this is the form of this polarization vector, which is normalized to 1 because of this condition. That is E star dot E is equal to 1. And looking at this vector, we can make the following educated guess. Kx, Kz, K, Ky, all these coefficients here in this formula can be replaced by derivatives. And that makes the whole Whittaker construction quite trivial. Namely, pulling out this outside of the Fourier integral can be done with the help of derivatives. So denoting everything else here that remains by chi, a solution of the wave equation. Here we have the following three-dimensional column. dx dz plus I divided by c, the derivative with respect to time, and the derivative with respect to y. These two animals represent minus kx, kz, because acting on the dependence on x, y, and z hidden in this factor, we exactly reproduce this. Here we have in the second row dy dz minus I over c dt dx. And here we have with the minus sign the two-dimensional Laplacian, which I will denote d transverse. The Laplacian with respect to the coefficients k, x, k, y. These derivatives are with respect to x and y. So we have followed the legacy of Whittaker, and we have indeed given f as a scalar function, just one function, and then we act with derivatives, which is quite simple, depending on the form of this function. So let's now see how this works, but before that, I may write this in a somewhat more general form. Namely, I can also say that f is equal I dt plus c and curl acting on a curl of some unknown function, call it phi, vector function. This is another way of approaching the Whittaker idea. Now, under what conditions this f will satisfy Maxwell equations? Let's see. In order to see that, I bring the right-hand side to the left, and then I get minus sign here. So in effect, I must check whether I dt minus c curl acting on this whole thing will give 0. So we have I dt here with the plus sign, c represents here, and the curl of this vector field phi. Now what happens here? We have the difference and the sum. So the result is that we have minus dt squared, the difference of the squares. First term is minus I, and that I that produces minus I, and then we have here minus, yes, correct, curl of curl and c squared, of course. Such an expression, we have to take the first curl and the second curl. There is a formula in vector analysis that says that curl of the curl just follows from the properties of the vector product. Then this is equal minus gradient of the divergence plus, no, the other way around. I have a minus here, yes. So we have plus gradient of the divergence minus the Laplacian. This is the straightforward application of the rules for vector products. And this part will not contribute because the divergence of a curl is 0. So we are left here only with the Laplacian coming from here. And the net result is that we have the wave operator. C squared here is in the second term, but I can divide by c squared. The wave operator acting on this, and of course it does not act on the derivative, it acts on this phi, and whenever phi satisfies the D'Alembert equation, the wave equation, I obtain from this formula the solution. What is the relation between this formula that looks a bit more general and this one that we obtained before? We have to choose some simple ansatz for phi. And the simplest one that we can imagine is a unit vector in some direction, let's say z direction, times a scalar solution of the wave equation. And if you choose this vector in the z direction, that's a simple exercise. You reproduce exactly the construction that I outlined before. So I also explained how to generalize this formula quite easily just by introducing an arbitrary vector solution of the wave equation. However, for our purposes, it will be sufficient to use this concrete formula. Other formulas are completely equivalent because we have a freedom here of choosing the phase of this vector E. We only assume that it's normalized, and by choosing various kinds of phases which are dependent on K, we can have a general method of constructing other solutions, which, however, will not be very useful in our analysis. So what is the simplest application of this whole construction? Choose just the straightforward plane wave, I omega t plus I kr. What will happen? Very simple. The derivatives will act. They will reproduce here the polarization vector, and we will have the solution of the plane wave type in the form polarization vector. This thing here for constant vector k, which is fixed now in this case, is just a number, some number, so it's not important to keep it. We can drop it, and this is our solution of the Maxwell equations. Well, to see what it really describes, I will write this expression here in spherical coordinates, and then the vector E becomes a function of the polar angle and azimuthal angle. And when you cancel or dimensional factors here, what one gets is the following. That's again a simple exercise for students. Spherical coordinates are the standard spherical coordinates that one learns in electromagnetism. And what we get here is minus, after, as I said, cancelling all terms, we get here cosine phi cosine theta plus I sine phi, and here minus sine phi cosine theta minus cosine I cosine phi, and here there will be sine theta. Obviously this must be dimensionless, because if it's normalized, cannot have any dimensions. And this is a simple way of seeing what is really happening. In physics, one usually takes the wave propagating in the z direction. There are some exceptions in some books, they propagate in the x direction. However, my favorite direction is z direction. In the z direction, I remind you what are these coordinates. The angle theta is measured from the North Pole. So in the z direction, cosine theta is 1, because theta is equal to 0 when the wave goes in this direction. And we obtain the following: 1 over square root of 2 here. And what is then minus cosine phi plus I sine phi? This is simply minus E to the power of minus I phi. And this term here will be minus I. I pull out minus I, so there will be e to the I phi. And 0 here, because I have chosen my propagation along the z direction. So we have such a simple wave, and you see the role of phi. Phi simply gives a phase to these two components. And much more familiar, since this is a solution for any phi, of course, I have chosen theta, so I can choose phi. So I choose phi in such a way, just to make life indeed very simple. I pull out a factor of before I choose phi, let me pull out the factor of e to the minus I phi in front, square root of 2. And then we have minus 1 here. And here there will be minus I, e to the twice I phi, and 0. Choosing phi as pi divided by 2, I obtain just minus 1 will cancel with this sign here. And we have now, apart from this phase factor, which should not be important because we can always multiply this wave by any amplitude, So the important thing is that we get the polarization vector minus 1 plus I0. And this polarization vector, I already said I dropped into the minus I5, gives you, when you separate F into the real part, the electric field, and the imaginary part, the magnetic field, the standard textbook solution in the form of the circularly polarized wave.
But the moment you took plane waves, your problem is not three-dimensional really, it's 2.5 in a sense. So you
yes.
could also use polar or cylindrical coordinates and you get the same.
Of course, yes, yes.
Same answer.
Just, I wanted to show that this formula looks nice in spherical coordinates. I could choose also cylindrical coordinates. So plane wave is easily reproduced, and now let's talk about this problem in somewhat more general terms, which will give some more interesting results. Well, you may say, well, what big deal for one simple plane wave? I can do it in many different ways. And I can always choose the direction in the Z, along the z-axis, and I get the textbook problem. However, if you want to do something more complicated, then the standard approach would not be so simple. For example, you have two plane waves. Then you cannot choose a simple form for both of them because they run in different directions. Here, however, the formula is extremely simple. It's one wave running in some direction fixed by this unit vector along some direction, and the other running in a different direction. And you can just take the sum, and you don't have to worry about solving the Maxwell equations. All you have to do is differentiate, and you have the result. And that brings me to the problem of a somewhat more general approach to this Whittaker program, one may say. Well, what we really did, oh, it's a pity I erased this. Let me write this again, the formula that I've given, I dt, and there was plus C curl acting on some curl. We have a solution of Maxwell equations generated from this vector solution. How does that fit the standard approach? This approach is also known, and this is called the Hertz superpotentials. What are Hertz superpotentials? Are two real vectors that give you the solutions of Maxwell equations by differentiation them twice. And this is exactly the formula for super Hertz potentials. If you ever encounter Hertz potentials, this is the way of looking at them from this point of view. This is the Hertz potential. You have to differentiate twice to obtain the solution of Maxwell equations. And the Hertz potential, of course, is a solution of the wave equation. Now there's another superpotential that is used in electromagnetism, and this is called the Debye potential. So we may ask the question, how do the Debye potentials fit into this scheme? They fit very, very nicely, namely I dt plus C curl acting on the following. I call it L times some divided by what is L? Well, it's an angular momentum operator using the quantum mechanical language. However, I drop h bar here because this is all classical. We don't need h bar. So L is simply a vector that has x dy minus y dx. I'm sorry. This is the z component. So this will be z component is x dy minus y dx, and the remaining components are obtained by substitution. Instead of x, now we can have y, so there will be y dz minus z dy, and here we'll have z dx minus x dz. This is the definition of this differential. And obviously, this expression replacing this one is also of the form which is needed here, namely the divergence must vanish in order to satisfy the Maxwell equations. However, the divergence of this vector is 0 because L is R cross nabla, so the divergence is again 0. And why are these solutions of the like interesting? Because they are useful for reproducing waves that emanate from some finite region. So you have the source here, which is oscillating and radiates waves. And if you choose phi in such a way that it correctly reproduces the properties of the source, you have the formula for the bipotential. So that this approach is quite universal. And
can you get also Leonard-Wiechert potentials the same way?
Yes, but that would be a bit more complicated because Leonard-Wiechert potentials introduce sources.
Yes, that's why I'm asking.
Yes, yes, of course.
And what would be the way to do it?
The way to do it would be go back to the Maxwell equations, substitute the sources here, and of course there is the source which is the source of the electric field, depending on the type of the source. A moving particle produces both electric and magnetic fields, therefore there will be source terms in this formula. And then what you have to do in this case is to work a bit backwards, namely to write down the Maxwell equations with the sources, and then to combine the electric and magnetic fields together. So now, let me do something different, again showing the usefulness of the F vector. That much we already know, that it's not needed. Let me now consider, probably remember that so I can erase this here. And let me talk a bit, perhaps I can or about monochromatic waves. Monochromatic waves are special in physics because they are very often produced by sources that involve transitions between atomic levels. Transitions between atomic levels mean that owing to the energy conservation, the wave emitted, if we forget the corrections due to the finite lifetime of these excited states, we can treat them as, roughly speaking, monoenergetic. And what is the solution of monochromatic type for Maxwell equations. First of all, we write this formula. There could be minus sign or plus sign here. Both of these cases are monochromatic. What is the equation that we get? It even has a name. Namely, there will be plus, minus, here k. I cancel the factor of c on both sides. So there's k, the length of the vector, times f here of r, plus, or equals, if I write it on the other side, plus the curl of the vector f. This is what is valid for the monochromatic waves. The curl of the vector reproduces the vector up to the length of the wave vector associated with the frequency that we are talking about. This equation has a name. This equation is called, we should value this name because it comes from a Czech theoretical physicist, Trkal. As quite often in the Czech language, they don't need vowels, they have consonants. So Trkal was the one who studied this equation, and that's an interesting mathematical problem. We have a set of three components of a vector, and the question is, what is the most general solution? What are the solutions of this equation? So we get the Trkal problem. We will not go into mathematics, but we will draw some conclusions from this, what we have here. So if we have any Trkal vector, fk, let's call it capital T, Trkal vector, and we multiply it by e to the minus or plus I omega t, we have a solution of the complex form of the Maxwell equations. Now, what does this mean for physics? Well, let's take the real part and the imaginary part of this expression. The real part will be the electric field. I now talk about the vacuum, so I will not distinguish between EB and DH. I will just use E and B here, even though in the definition of F I introduced D and B. This will be now E. So E is the real part. I will drop also the square root of 2, which does not matter in the general case. So we have E of R and T is equal to cosine omega t times the real part of the Trkal vector, the real part. And the second term will have either plus or minus sign, depending on the sign over there, sine omega t, and the imaginary part of this Trkal vector. And for B, we have R of t, and just cosine and sine are at different places, minus plus. Now I'm taking cosine omega t and the imaginary part. And here the imaginary part of this also has the term sine minus plus sine omega t and the real part. Now, what are these real and imaginary parts of the trickle vector? They're components of the electric field or the magnetic field taken at time t equals 0. So I can also write this down in the form cosine omega t times the electric field at the time 0, which is a function of r, plus minus sine omega t, and here is the magnetic field at time t equals 0. And here the second formula is minus plus altogether cosine omega t b of 0 and r. Of course, something must be fixed here. This must be multiplied by c, and this should be divided by c to make the dimensions match. So it's sine omega t E0 of r divided by c. What is the physical meaning of these expressions that I obtained? At each point, the electric vector and the magnetic vector trace an ellipse, because that is a parametric representation in analytic geometry of an ellipse. When t runs through full cycle, we get, here are these, we have these two vectors. No matter how they are oriented, they are two vectors, and the field is in the plane defined by these two vectors, and one of these vectors traces some ellipse, and the other vector traces some ellipse. So for any electromagnetic monochromatic field, this is the following structure. The electric field goes around the ellipse, and magnetic field, there's no more general solution than that. All monochromatic solutions obey this at each point. Of course, what makes these solutions quite different is that at different points the ellipses are different. But at a fixed point, when E of r is given and B of r is given, we have just two ellipses. And this comes out, as I have shown quite easily within this formalism. Needless to say, you could reproduce this also from Maxwell equations, but it will take a bit more doing. Okay, so what else we can say here that is of some importance in optics? There are the so-called Bessel beams, which are very popular because they carry angular momentum, as I will discuss a bit later. And what are Bessel beams within this formalism? Well, we take the simplest possible solution involving a Bessel function. And this solution is take some Bessel function of k rho multiplied by e to the minus I omega t and multiplied by I kz. Kz times z. So what are the numbers here? No, I'm sorry, I should have written here. K perpendicular. What is the meaning of these parameters? Here I have the solution, chi, solution of the wave equation, because when you substitute this into the wave equation, you notice that the equation for the Bessel function is exactly the one that the Bessel function obeys. So this is a solution of the wave equation. It's a function of r t Oh, I didn't say that rho is the square root of that square root. So this solution. I'm sorry. Yes. Yeah, I know you. We need also the factor of Im5, otherwise this would not be the solution of the wave equation. And this solution is parametrized by the following coefficients. There's frequency omega, there is the z component of the wave vector in the z component of the wave vector, and there is the value of the perpendicular component of the wave vector, and the index m here, which is an integer and tells you which order of the Bessel function we have. And this is the simplest way that carries angular momentum.
In free space.
In free space. And also in a medium, if the medium is
but then you
homogeneous.
have to add the solution is more complex. I believe you had to have also
no boundary conditions.
Okay.
If it's a homogeneous medium, then it will be the same. With boundary condition, you will need to satisfy in the fiber the boundary condition as the edge of the fiber. Now again, if this is something where really this approach is very convenient. Suppose you want to write the solution of Maxwell equations representing a Bessel wave. That is really a complicated problem. Because, as you can see from this solution, there are complications of the following form. Remember that in order to obtain solution of Maxwell equations, we have to differentiate. When you start differentiating, it's easy when the differentiation is with respect to the exponents. But when you start differentiating the Bessel function, and you must, then you obtain other Bessel functions. And the formula at the end becomes quite cumbersome. We have combinations of Bessel functions, etc. Whereas this solution has just one Bessel function. But this Bessel function becomes multiplied and becomes two Bessel functions when you start different. There are the corresponding formulas that give you the derivatives of Bessel functions, again as a sum of two Bessel functions. So other functions can also be obtained from some simple solutions. And let me give you one more example, which is quite neat, because it shows you a certain formal connection between Maxwell equations and the Schrodinger equation. Let me go back to the wave equation, and let me write down this equation in the following form. 1 over c dt minus dz 1 over c dt plus d over dz minus the perpendicular part of the Laplacian, which is left when I take out the z derivatives. And this is supposed to give 0. Now suppose we look for periodic wave solutions with respect to this variable. So if the period is defined by some coefficient omega, then this becomes I omega divided by c, and then we have 1 over c dt plus dz. And let's call this the new time variable here. So we have 1 over c, and there is some new time variable, let's call it tau here. which is the combination of the time variable and the z variable. And after that, you notice that lo and behold, we get the Schrodinger-like equation. I leave the derivative with respect to tau on the left-hand side. And on the right-hand side, I have the perpendicular part of the Laplacian, and I have the omega and c squared, so c squared is in the numerator, omega is in the denominator, and this is precisely the Schrodinger equation with some identification of this coefficient here in 2 dimensions. Now, there are many obvious solutions of the Schrodinger equation in 2 dimensions. One of them is a Gaussian. So, if you look for the solution of the Schrodinger equation in the simple form of a Gaussian function, then you are done and you get a solution of Maxwell equations. This leads to the so-called, to many other solutions that are known and used, in particular to something which is called Gauss-Laguerre or Gauss-Hermite solutions of Maxwell equations. All these solutions, unfortunately, are sick. They are sick for the following reason. Tau is the combination of t and z, and this combination also enters here, is t minus z. So you have always the waves, since you fix this dependence, you have also waves running in the opposite direction. So why are these solutions of Maxwell equations so popular? Because people working in optics don't care too much about this sick behavior because they consider these beams as being focused, and this is the so-called paraxial approximation. You have this beam that runs here, and they say, wait, we only need this beam here very close to the axis. And then you can show that the dependence that describes the wave running in the opposite direction drops out in this approximation. So these waves are very popular. When you take at random a paper on modern applications of quantum or classical optics, you always encounter these Gaussian-like beams, either Laguerre-Gauss, or that depends on what are the polynomials that multiply the Gaussian function. But as long as you stay close to the axis, they're okay. However, you must be careful because waves, as you know, disperse. You cannot keep them always confined to a certain range near the symmetry axis. So after a while, the paraxial approximation will not be correct. But you may say, wait, you have given us this Bessel beam. This Bessel beam does not disperse because rho enters here, and if you plot the dependence on the rho, it is not time dependent. Bessel function, depending on which Bessel function you choose, it will have these decreasing flux oscillations, and it stays always the same. So how come I'm telling you that the waves disperse always, and you cannot have dispersion-less propagation? How come Bessel beams do not have this property, and they are called non-dispersive beams? However, the price you pay for the Bessel beams to be non-dispersive is very high. These beams are non-physical for the following reason. When you find the energy that is transported by such a beam, the energy is infinite. That is the price you pay for having non-dispersive beams. Since the beam has infinite energy, it is not a physically realizable beam. When you cut it off so that it will carry finite energy, it will start dispersing at the edges. So there's no way to avoid dispersion, and there are two ways of doing it. One is going through the Gauss-Laguerre beams, and then you say, my approximation fails after some time, t, when the beam runs away. And if the time b is, say, 10 to the 8 of a second, then you have meters that characterize the distance that the wave travels. So you have, if you have an optical table, and if you are careful, then on the optical table the dispersion of the wave can be neglected. When you use the Bessel beam, then you must be careful about the energy that is carried by this. You must cut it off, and then life becomes even more complicated. Okay, I think, let's see, there's something else to say. Aha, there is one, two, well, perhaps two things. First of all, a general remark, proving again the convenience of using the Riemann-Zilberstein vector. That I have already mentioned before, but now I'll come back to this. The energy of the beam is given by the integral of f star f, and the momentum of the beam is whatever is c d 3r f star cross f. So when you are interested in such global properties like the total energy or the total momentum, you don't need to go through this complicated process splitting the f vector into its real and imaginary part, which is cumbersome. If the beam has the imaginary unit at various places, the expressions become complicated. However, for the energy, you don't need separately the electric and separately the magnetic field, and the same for momentum. You can use the full f vector. All you have to do is calculate f star, which is done, of course, by reversing the sign of I in the formula, and that's it. And this gives you simple formula for the total energy, total momentum. Well, there is the whole area also that is quite interesting. That is the study of vortex lines of the electromagnetic field, because vortex lines in free space, there are no sources of the field, therefore D and B obey the divergence condition, and that means that vortex lines cannot end, they always must close. And when you have a solution that is a bunch of these closed lines, you may expect that such a solution will have some stability properties because of the fact that you cannot break these vortex lines. And some people even try to use such solutions to describe the ball lightning. Ball lightning still does not have a well-developed theory, but of course that effort failed, because we know that ball lightning involves not only purely electromagnetic field, but there is a lot of plasma in it. And plasma coupled to electromagnetic field is not such a simple medium.
Chapman understood that all this.
Yes, all
lines,
this
yes.
stuff comes then, and it's not quite. And I don't believe that you can have a simple solution of the ball lightning using only the solutions of Maxwell equations. One more remark of constructing solutions is the following. You can take this chi function as a function of r on the length of the vector d. So this will be a spherical wave. And in order to make this solution of Maxwell equation, you can do the following trick. You take a function g, which is a function of ct minus r divided by c minus g t plus r divided by c, and all that is divided by r. Such a simple trick will do. G can be an arbitrary complex function. No restrictions whatsoever, except that you should be able to differentiate this function. This function is regular because when r is 0, then the numerator vanishes and the denominator vanishes, so the zeros cancel. And G in general will be complex. So you can have all kinds of nice solutions in the form of spherical waves, including such typical spherical waves as those described by the sine function. This happens when you take G in the form of sine kr divided by r, then you get spherical waves well known in the sine form. So there are many tricks you can play, but my time comes to an end. With generating solutions and only your imagination here is a limit what you can get. Next time, as I said, I will give the quantum mechanical treatment. That is, the electromagnetic field will be quantized, and I will again try to convince you that this approach is quite simple and you don't need any canonical formulation, any Poisson brackets or whatever. You just can guess very easily, just using Planck, I may say, and from Planck formula that the energy of the photon is h omega, you can deduce full general quantum theory of the electromagnetic field. Thank you.